are in Introduction to Statistical Learning. We're just starting Chapter 6, so we're on the very first question. It's a conceptual question. And this chapter has to do with how do we select variables in our statistical model given all the combinations of possible things we could use to try to predict an outcome. Which ones does it make sense to use? That's kind of what this chapter is getting at. And so this first question deals with a few approaches called best subset selection, in which every combination of variables is tested and then you simply select the best one. The problem, though, is that after a while there's just simply too many combinations of variables to be computationally feasible to run. And so there are other algorithms such as forward stepwise and backward stepwise, and then there's also a hybrid where you're forward stepping and or backward stepping at each step. And the way that these two algorithms work is your model first picks the variable that has the most drastic reduction in some kind of fitting calculation, such as AIC, and then it selects another one and another variable in addition to the one that you just had, and it selects the next variable that again improves that fitting metric the most, and then it continues until it can no longer improve that fitting metric, whatever that happens to be. Okay, and in forward stepwise, you are adding one variable at a time. So you start with none and you add one at a time, and then with backward stepwise, you start with everything in the model and then slowly peel one off one at a time. Okay. So here's the question, and it has three parts here, and then part C is a bunch of true and false questions. So we'll just go through these at a time, one at a time. But let's just read this. So we perform best subset, forward stepwise, and backward stepwise selection on a single data set. For each approach, we obtain P+1 models, okay, containing, up to P predictors. Okay, explain your answers below. Okay, so let's start here with part A. So it says, which of the three models with K predictors has the smallest training RSS? The three models that it's referring to, I believe, are the model selected by best subset selection, the model selected by forward stepwise, and then the model selected by backward stepwise. Okay. So again, which three models with K predictors has the smallest training residual sum of squares? Okay, so I think that this is maybe a little bit misleading, because if you remember my explanation of what these, well, at least forward and stepwise, what these are doing, well, and I guess best subset is in order to select the best model or the most appropriate model given the algorithmic path of these two, it is comparing something like AIC or BIC or R squared, the adjusted R squared, and all of these are estimates of out of sample data. So in other words, it is an estimate of fit to test data, okay, not to the training data. Okay, so again, these different methods are trying to select based on their estimate of what will work best on unseen data, not on the seen data. Okay, so in other words, on the testing data. So I could be wrong here, but I think then that means that any one of these model selection methods could produce the lowest training RSS, simply because none of them are optimizing for training RSS. And so whichever one produced the lowest training RSS really would be incidental, I think, or roughly incidental. So anyway, I've seen some other answers where they say, oh, well, clearly it's best subset because, well, it's picking the best model. But again, best is being defined by an out-of-sample estimate, out-of-sample fit estimate, not on the training data. So I think that I'm correct here, but let me know if you think differently. Okay. Part B, which of the three models with K predictors has the smallest test RSS? Okay, so now what we would expect to be the case um, is that best subset method should have the lowest uh, residual sum of squares on the test data, simply because it has tested all models, right? And so all possible models. Now, there is a little bit of a problem with this because, well, okay, on average, we should expect best subset selection to work. Now, it's not to work best. Now, it's not guaranteed that it will produce the smallest test RSS because, again, it hasn't actually been trained on the testing data, and it could be by, just peculiarities in the data that one of the other two methods happens on a single run, on a single set of variables, on a single data set, just happens to produce a better model. But on average, we should expect that the best subset selection is performing best. Okay, so now we have several true and false questions about these three algorithms. So let's go through them. So the first one, the predictors in a k variable model identified by forward stepwise are a subset of the predictors in a k plus 1 variable model, also identified by forward stepwise selection. Okay, so this one I think has to be true because the k plus 1 variable model was built off of the best k variable model, right? And so in forward selection, there's no option of removing variables. So once you get to the best k variable model, if there is another variable that is appropriate to add, it will only add it to the best model that has been attained with k variables, right? It's building off of what was there before. It's a greedy algorithm, okay? So that one should be true. So number two, or part two of part C, or whatever. So the predictors in a k variable model identified now by backward stepwise selection are a subset of the predictors from a k plus 1 variable model also identified by stepwise selection. So again, this one I think has to be true because, so again, in backward stepwise selection, we start with all of the variables and then we peel one off one at a time, okay? So that means that if we start with all of the variables, well, eventually we're at k plus 1 variables, and so if we're going to peel one off, then the resulting model is going to have all but one of the variables that were in the k plus 1 variable model. Okay. All right. Part 3. So the predictors in the k variable model identified by backward stepwise selection are a subset of the predictors in the k plus 1 variable model identified with forward step selection. Okay. So this one, it is not necessarily true. This is probably a false statement. It may be true in some circumstances, or by happenstance. Okay, but the two model, or the forward and the backward stepwise selection methods, they start at different starting points, either with no variables and then they start to add them, or with all the variables and start to peel them off one at a time. Okay, and so every time that they're going to make a new model selection or a new variable selection to either add or subtract, they're starting at different points here, okay? And because they're greedy algorithms, their base model before adding another variable or subtracting another variable are going to differ. So the selection method, whether adding or peeling away one of the variables, is always being compared to a completely different base model. Okay, so there's no reason to think then that these two, that forward stepwise and backward stepwise, will always converge to the same subset or to the same set of models as they work their way through their algorithm. Okay. Okay, part 4. So the predictors in a k variable model identified by forward stepwise are a subset of the predictors of the k plus 1 variable model identified by backwards. Okay, this is false for the same reason as in 3 here. Okay. And now the last part. So the predictors in a k variable model identified by best subset selection are a subset of the predictors in the k plus 1 variable model identified by the best subset selection method. Okay, So this one is also false. Okay, so the reason is because the best subset model is not a greedy algorithm, right? So in other words, its choice of well, first of all, it doesn't have a path through through this variable selection space. Okay, it tries out all possible models. Okay, so that means that no model is being generated based on any path through this variable selection space. They're all being compared to one another. Okay, so so again, there's no reason then to believe that that the best k variable model is going to just be a subset of the k plus 1 variable model, because the k variable model did not inform the k plus 1 variable model. Okay, that's not how it happened, right? So we didn't take the best k variable model and then find the best k plus 1 variable model, or vice versa. Okay, we tried all k variable models and all k plus 1 variable models, and then we just happened to see which one worked. Okay, so anyway, so I hope that makes sense. It should if you've read the chapter, and we'll call that good.